Assalamualaikum warahmatullahi wabarakatuh and good day. So in this video, we'll continue with theorem 7.3 that we've discussed in previous video. But here we'll show you how to prove it. Okay. So again, if you look theorem 7.3, we talk about when we have y1, y2, yn is a random sample from normal distribution. And then with mean mu and variance sigma square, then you will have this one. Okay, you will have this one, which is n minus 1 times s square divided by sigma square. This one is also similar with 1 over sigma square. And this one will give you y1 minus y bar square, summation of from 1 until n. This one has a chi-square distribution with n minus 1 degree of freedom. Okay, and then y bar and s square is are independent random variables. Okay, so this is the proving. So for sure, you can have a complete proof of this theorem is outlined in exercise 13.93 letter. Okay, in your textbook. So in order for us to make the general result more plausible, okay, in this proof we consider n equal to 2, okay, and show that n minus 1 times s square over sigma square has a chi-square distribution with 1 degree of freedom. Okay, so now we have case n equal to 2. So when we have n equal to 2, your y bar, okay, from previous theorem, you can see that y bar is what? Summation of I from 1 until n divided by n. So that's why you have here, okay, 1 over n, y1 plus y2. Okay, and then from previous s square, you also have this one. Okay, s square equal with this one. So you can have this one. 1 over 2 minus 1 because your n is equal to 1. And then this one, yi minus y bar square. And then your I is from 1 until 2. So this one you substitute. What is your y bar? Okay, so this one actually, if you break the bracket here, you can have 1 over 1. Okay, here will be y1 minus y bar. Oops, sorry. Y bar. Okay. So this one will be square plus y2 minus y bar. So here square. Okay. But what is your y bar? From previous, you have this one, isn't it? So here, that's why you have y1 minus y bar is 1 over 2 times y1 plus y2. Okay. Square. And then plus y2 minus half y1 plus y2 square. Okay. You replace the y bar to here. Okay, this one should be here lah. And then here will be here. All right. And then this one you simplify. Then you get this one. And then you break the bracket. And then you simplify again. You will get this one. Okay, here. Okay, here actually you will have 2 y1 minus y2 square over 4. So that's why you simplify this one. You get here. All right. Now it follows that when n equals to 2. All right, when n equal to 2, you have here n minus 1 s square sigma square. So here you know n equal to 2, so you have 1. So s square is what? S square is this one. So you substitute here. Okay, and then you have this one. And then you try reconstruct this one becomes z square. You can see that y1 minus y2. When you square this one, okay, here you need to square root lah in order for you to get this one back. Okay, so this one will show that this quantity is equal to the square of standard normal random variable. Okay, because z square here. And then we already shown this one in example 6.11, which has or possesses a chi-square distribution with 1 degree of freedom. Okay, so now here, if you look, y1 minus y2 is a linear combination of independent normally distributed random variable. Okay, how is it? This one, y1 minus y2 is equal with a1 y1 plus a2 y2. So you can see that what is your a1 is 1, and what is your a2? Negative 1. All right, so by theorem 6.3 that you've done before, you have learned before, tell us that y1 minus y2 has a normal distribution with mean this one. Okay, do you remember when you find the expected mean? Okay, y1 minus y2 tu. Okay, you know that y1 you have mu, and then here you have negative 1 mu. So this one it becomes 0 lah. And then for variance, similar, expected variance for normal distribution is sigma square. Then here you have a1. So you need to square because this is variant. And then you substitute the value, you simplify, you get 2 sigma. So therefore, that's why you will have this Z. Alright, so this Z is follow normal distribution. Okay, and then because you have n equal to 2, okay, so that's why it become like this. Okay, we have this one, so this one becomes Z square. So that's why here you can see that it follows chi-square distribution with 1 degree of freedom. Okay, because from here that you can see n minus 1 is 1. So 2 minus 1 is 1. So 1 degree of freedom. So you can see also this one in example 6.13 that we've proved that u1 equal with y1 plus y2 divided by sigma, and then u2 equal with y1 minus y2 over sigma, and then this is an independent random variable. Okay, and then remember you have n equal to 2. So here basically you have y bar equal to this one. So this one you can substitute with sigma u1. How is it? So if you look here, you have u1 equal to y1 plus y2 divided by sigma. So this one, sigma u1 equal with y1 plus y2. Alright, so this one you can replace with sigma u1. So similar for this one as well. Okay, that's why you will have this one, sigma u2 square over 2 for s square, and this is for y bar. So because y bar is a function of only u1 and s square is a function of only u2, so you can see that it's independent, isn't it? It's different. So this one shows that y bar and s2 also independent. Okay, this is to show that y bar and s square is independent. But this one to show you that when we have this one, okay, okay, y1, y2 until yn is from a normal distribution with mean mu and variance sigma, and then we have this one. All right, so based on this one will give you chi-square distribution with n minus 1 degree of freedom. That means if you prove here when n equal to 2, okay, it's become chi-square distribution with 1 degree of freedom. So let's say if you have n equal to 3, so n 3 minus 1 is what? 2. So this one will become chi-square distribution with 2 degree of freedom. Okay, so that's but we show you using n equal to 2, so for you to see how is it. Okay, so now we look example 7.5. So example 7.5 we follow from example 7.2. Now the ounce of fill from the bottling machine are assumed to have a normal distribution with sigma square 1, the population variance equal with 1. And then suppose that we plan to select random sample 10 bottles. So you can see that your sample n is equal to 10 and measure the amount of fill in each bottle. Okay, so these 10 observations are used to calculate sigma s square, sample variance. Okay, it might be useful to specify an interval of value that will include s square with high probability, which is here they use 0.9. So find the number by B1 and B2. Okay, so this is s square. Okay, because we want to measure the sample variance for s square. So now when you want to find this one, okay, actually this one is come from here. Okay, you remember that your s square is what? N minus 1 s square divided by sigma square. Alright, so here also you will have n minus 1 beta b1 divided by sigma square. And then because of sigma square is 1, here is 1, 1, 1. So you will have n minus 1 s square. Alright, so this one shows you this is what? Chi-square distribution with n minus 1 degree of freedom. So therefore, when you use a table, okay, your statistical table from previous applied statistic class, okay, it page 35, okay, page 35 for chi-square distribution, okay, page 35, okay, chi-square distribution, or maybe you can use this one, table 6 appendix 3, using the textbook that we use, okay, to find two numbers A1 and A2. And remember, because this is chi-square distribution, okay, you should remember that you don't have symmetric figure, you have skewed to the right figure. You have right, here is alpha over 2, so here will be 1 minus alpha over 2. And then if you look here, 0.9, you know that your alpha is what? 0.1. So when you divide by 2, here will be 0.05, here will be 0.95. Okay, so now we want to find A1, B1 as well. Okay, A1, B1, A2, B2. So using the statistical table, again, page 35. Okay, in your statistical table and formula. So one method of doing this is to find the value of A2 that cut off an area of 0.05. Where is it? Which is here. This is A1. Okay, sorry, this is the A2. And then you have another one is A1 is here, is here. Okay, so here is 0.05, here is 0.95. Okay, because 1 minus alpha over 2 and the right side is alpha over 2. And then remember that your degree of freedom is n minus 1. So which is 10 minus 1 is 9. So now look your table, your statistical table, page 35. You look new. Okay, your degree of freedom is equal with 9. And then look this one, 9 and then 0.05. You get 16.919. Okay, and then look, so this is the side here. Okay, and then this one 0.95. Look 9, you will get 3.325. Okay, 3.325. If you look here, let me see back again. Yep, 3.3251 actually. Okay, but this one they use 3 decimal places. Even here, 919. Okay, this one 9.90 lah. Okay, doesn't matter. Okay, so this one you will get A1 and here is A2. Okay, now you know that A1, A2 equal with this one. And then here you know sigma square is 1. Here is 10 minus 1 is 9B1. Okay, so and then this one similar, you get 9B2. Then when you rearrange this one, you will get your B1 equal to 0.369 and then B2 is 1.880. Okay, so if we wish to have an interval that will include S square with probability 0.9, okay, the interval is between 0.396 and 1.880. That means the S square value is in between this interval. Okay, so it's quite wide lah. You can find the range here, kan? The range is equal with what? 1.88 minus 0.369. So you can see it's quite wide. Okay. So, the result given in Theorem 7.1 provide the basis for development of inference making procedure about mean of normal population with non-variance sigma square. Okay, so in that case, Theorem 7.1 tells us that square root n times y bar minus mu over sigma has a standard normal distribution. Okay, however, when sigma is unknown, okay, it can be estimated by S. Okay, sample standard deviation which is equal with sigma square S square. And then the quantity become like this. Okay, instead of sigma, we have what? S here. And then provide the basic for developing method for inference about mu. And in the next slide, or in here, in the next video, we show that this one has a distribution known as student t distribution with n minus 1 degree of freedom. So the general definition of random variable that poses student t distribution we'll discuss in the next video. So you just recall back from applied statistics, okay? You learn confidence interval, isn't it? You have mu. All right? Confidence interval for 1 mu, 2 mu, pet mu, okay? So if you have 1 mu, for example, when you know your population variance, or if you know your standard deviation variance, standard deviation population, okay, if you know this, you will use Z straight away, okay? But if you are talking about sigma square only, you will have chi-square distribution. Okay, this one Z, which is normal distribution, isn't it? Now, when you didn't know this one, you only have S, so you will use T distribution. Okay, so that's the correlation between how it can be correlated to each other. Okay, well, so we'll discuss later. So thank you, class.